Good morning, mathematicians. I think this started correctly. Uh, I think this started correctly. Let's find out. I'm experimenting with scheduling this, and oh, the BIOS. Is this more content for me to react to? Probably not. It's probably just a normal video. Nice. Okay, sweet. The fundraiser button is attached to it. Okay. This is not the 8 hour marathon live stream, but this is a test for that. So, but by all means, feel free to donate. Anyways, yeah, I think this Saturday is gonna be it. 8 hour math marathon charity live stream event. Hello, Baobab Tree. I think I said that more correctly today than I did before. Oh man, I meant to iPappy. uh, um I meant to solve that problem. Um do I embarrassingly look back to this basic algebra problem that I didn't solve yesterday? And try to make my brain think more good again today? I don't know. I guess that's what I'll do. Where were we? What were we trying to prove? Yeah, we took the set of so we supposed we had an integral domain and all the primes were principal ideals, and we let n be the set of non-principal ideals. We argued it was bounded above, and so there had to be a maximal element by Zorn's lemma. And what did we say about that maximal element? Well, we wanted to argue... we wanted to obtain a contradiction, right? So this ideal should not be principal, and we're trying to cook up a contradiction. However, basically, what is it? A should be principal, as should MB. Right? Because we should have an AB. We should have an AB. Where were we here? We should have an A and B, which their product is in M, but for which neither A nor B is in M. And so, therefore, we have that M is contained in the principal ideals. Good morning, Raymond. Good morning. Do mathematicians make a distinction between sheaves in the context of Grothendieck, topoi / a Talco homology, and the concept of a bundle or fiber bundle? Yes. Well, fiber bundles are just not sheaves. But if you take, if you have a fiber bundle, then you can form the sheaf of sections. So over the open set, this will be the sections. This will be the sections of your bundle. So there's a connection. And in fact, how does it work now? You have some vector bundles in particular, I believe sit inside the category of coherent sheaves. Well, what do I mean by sit inside? Not actually, because a vector bundle is not a sheaf. But if you take the sheaf of sections, then it should be a coherent sheaf, I believe. Okay, so A times B is in M. Right. So it's contained in these two principal things. But we know, what else do we know? I mean, AB is in M. So M is the ideal generated by A and B. Ain't no doubt about it. Ain't no doubt about it. Okay. And then what about the product? The product of these ideals will also be a principal ideal. But this is just the ideal generated by these three things. And I don't know what else to say. Yeah, I don't know what else to say. What's the plus goal here? Oh. Is there a in chat? Oh, is there? I missed some comments. Oh, Nerdy Quigsire, I missed you saying hello. Good morning. Yeah, so I set this to be a charity stream, but it's not quite clear. Do you guys have like a donate button or something there? I'm just trying to make sure this is set up for when I do the real deal. Whoa! For when I do the real deal. Okay, see, it does say fundraiser underneath. When I do the real deal. But, let's see. Oh, okay, there is. There's a little button, donate now. Okay, great. That is awesome. I should be using this other account to follow my own, just to give myself more viewers. This is not the 8-hour stream. But this is my test for the 8-hour stream. I just wanted to make sure that I could correctly schedule things ahead of time and make sure the donations are all set up and everything. But so I figured once I can make sure I got that going, then I think I'll start like officially advertising it for Saturday. So, Saturday. That's the plan. Saturday. The fundraiser, it will be the 8-hour stream, but I set it up anyways. So I mean, if you want to donate money now to the kids, then go ahead. Okay. Man, I really wish I had thought about this problem for like 2 seconds before I started streaming, so I don't keep looking like an idiot. 8 hours of math, that's the plan, baby. I mean, I'll probably have to like get up to go to the bathroom once or twice and like eat some food on stream, so I guess it will also be a mukbang. You used to be a kid once? Nerdy Quigsire, you still are a kid. Only 8 hours of math, yeah. Yeah, only. Maybe one day I'll do more. I don't think like it's probably not good for you. It's not good for me to sit still for 8 hours in front of the computer. So I feel like that's my limit, 8 hours is something. Okay. Anyways, we need to figure out why M is principal. Why is M principal? Ah, well, this ideal is prime. Hang on. This ideal is prime. So actually, this ideal is should be prime. So actually, R itself should belong to this ideal, and so it should actually be equal to one of these generators. You did not solve this problem, by the way? Okay, good. That makes me feel slightly less dumb. GF, are you saying I'm your GF? Or are you saying I'm your Galois field? Man, I gotta start making some Valentine's Day math cards or something. You're not allowed to donate, Locke? Really? Why not? Is it because of like your country, or there like regional restrictions? That's really annoying if so. That's really annoying if so. You thought you got it in like 2 minutes, but it turns out it got you in 2 minutes. Yeah. We are ring theorying, by the way. Sorry, you can't donate in this country or region yet. Lame. Lame. Damn, that's lame. Yeah. Well, sorry to hear. I mean, just do me a favor then and donate if there's some local children's hospital type charity. Just donate to them whatever you would have donated instead. How about that? We'll just take your word of promise. You were recording a video explaining the solution. You realized you were wrong. Oh my god, Nerdy Quagsire, you know what a ring is. You know what a ring is. It's an abelian group together with a monoidal operation that distributes over the abelian group. Something you don't have. Hey, I have a ring. Is this what you're talking about? I have a ring. Don't come at me. Don't come at me like that. Right. So this is the contradiction, though, isn't it? Because now, wait, no, this isn't a contradiction. Well, but this says that MAB is equal to MA. That's not really a problem, though, is it? That's not really a problem. Okay, but if MAB is equal to MA, then that means that B can be written in terms of elements in M and A, and that means A times B can actually be written like this as well. And so really this should be this principal ideal, right? Should it not? Is that it? Also, no? The group objects in AB are exactly abelian groups themselves, actually? Oh. Group objects in AB. Yeah, group objects in groups are abelian groups. Group objects in groups are abelian groups, but group objects in AB? Yeah, I guess you just use that same proof. It's not. I don't get equality here. Yeah, I just have containment here, but why don't I? Oh, cuz I guess I can't necessarily subtract off these elements. Right? This just becomes no, that you're right. That ain't true. Wait, MA times AB equals M. Right, yeah, that ain't true. Yeah, necessarily. Oh, okay. Yeah, here's the part of the show where we just give up. If Leo didn't solve it and I didn't solve it, here's where we give up. The original problem asked to prove that every ring, every integral domain in which all primes are principal, implies that every ideal is principal. Implies that every ideal is principal. Yeah. Do any of you remember first learning about y equals mx plus b? You distinctly remember learning about that as a child, being bewildered by it, and then literally moment it sort of felt like an awakening. I remember I was a theater kid in high school, and I remember, but I didn't have very large parts. So I was, just backstage a lot of the time in the wings, like waiting for my part. And so I would be working on math. Of course, I was failing high school calculus at the time, but in my free time, I was trying to learn like special relativity, and I was trying to generalize. This to y equals mx plus b to higher dimensions. But I failed miserably. But I filled notebooks and notebooks trying to come up with my own way to generalize it. You're just wondering if professional mathematicians have similar experiences? Yes. Like I said, I am just an addict. I'm chasing the dragon of those first hits of aha moments, and every once in a while we get them again. You talked with someone and you got the solution, but then you forgore. Oh no. Think about it geometrically helped. Zero divisors, reducible, tighten the gap. If M is any AB enriched category, then it behaves enough like AB that we can consider its monoid objects as internal rings. Okay. You think that is what you were thinking of? Classical and lab, just a bunch of language not helping people understand things. Yeah. So, anywho, I don't know. Do we try this again ourselves or do we just give up? Just give up. Just give up. If you don't understand what NLab is saying immediately, then you might have an issue. Yeah. Yeah, skill issue. That's what it sounds like. We could also try and create a chain of ideals, right? Like, consider like a chain of prime ideals in our ring. I don't know. I should try proving group objects in AB or abelian groups. Well, you're talking to me or you're talking to Locke? Is it? I mean, I don't know. Like, I think if you just unpack it through definitions, are you really using Ekman Hilton? I don't know. Integral domain in which all primes are principal, then all ideals principal. Let's go see here. Talking Locke, but you think Locke might be busy Googling definitions of random things. Right. Right, that thing was not principal. What are we doing? Uh-huh. Yeah, here's where we were. Alright, suppose these are both principal. And let n be the ideal generated by A? Why are they writing it like that? Oh, such that, the ideal, such that all RA are in M, which is also larger than M. Is it now? Excuse me? Why is this larger than M? Why is this larger than M? Why is every element of M in here? Unclear, I would say. If you told me this, I would say unclear. The guy who commented's proof was cool. The guy who commented. The guy who commented. What are you talking about? The guy who commented. I don't know what you're talking about. Use the colon ideal? What? Excuse me? What are you saying about my colon? You want to figure it out, you're muting me. That is fair. That is fair. That is fair. I highlighted this comment on last stream. What? Excuse me? Huh? I highlighted a comment on last stream? What are you talking about? No, but why does this contain M? Why does this contain M? This makes zero sense. Why would this contain M? And then they argue that the product is contained in M? This is also unclear. This is also unclear. Okay, let's go to someone else's answer. We can prove it using some machinery. Beautiful paper. Given an ideal, define... this is what you mean, the colon ideal. I see. Well, AM is in M. A times M is in M. Oh, right. Sorry. Okay. I'm back on board. Therefore, it's principal. Sure. So why is this true? Here's where we went wrong. When I wrote, I went wrong, but I think maybe I made the same mistake. When I wrote this, I suppose this product is actually M A M B A B. So that was the boo-boo. We were on the right path. But we just made a little boo-boo. That's what happens when you don't go slow and write things out rigorously and carefully. I suppose. That's how it goes. Noob versus pro versus hacker. Wait, who's what? Who's what in this case? Who is what in this case? Yeah. Well, that's basically the crux of the matter right there. Right, and then it's a product of principal ideals and thus principal. Yeah. Wait, why is there a step 5? Isn't that the problem already? Okay. I guess we still need to show that it itself is principal. Right, because we just argued that the product is principal. X is equal to S alpha. I think they meant to write A there. And conclude that M is principal, a contradiction. Oh, I see. And then they put it up against N. But there is an extra step here. They're putting it up against N, which is this colon ideal. Why is that principal, though? Why is that principal? I mean, are they making two statements, equality and principality? X being here, since this, we know this. Wait, why? Wait, what do they mean by alpha? Is alpha not a typo? No, alpha is not a type. Alpha is the generator of this guy. Right. Okay. I see. I'm the noob. Math Stack Exchange is the pro. Terry Tao is hacker. Okay. Good to know where I stand. Yeah. Okay. Well, I'm glad we looked this up. It probably would have taken me a little while longer to get that. TBH. This is too much ring theory for your puny brain to understand. I don't think that's true, Luck. I think you could understand every step of this. I mean, ideal theory is like ring theory, and it's all kind of the same. If he is a noob, your math undergrad is nothing. Well, we are all dust. We're all specks of dust in the vastness of the universe, and we all collectively understand 0% of the math that exists. Why letters? Where is the numbers? We've left the numbers behind. We've evolved past the need for numbers, Wes. And you have to use a colon ideal to make sure that your product of ideals is not too big. In terms of varieties, well, I mean, yeah. I mean, actually, that is interesting. Yeah, maybe we should have thought about things more geometrically, but oh well. Spec Armod I is reducible if I is not prime. Yeah. That is probably what we should have done, is thought more geometrically. But you know what? Whatever. We cheated, and that's fine. That is fine. Let's go have a look at what's going on in archive these days. You can't even visualize spec of anything properly? Well, why aren't you addressing that issue? Let's go fix that right now. If you're cognizant of the fact that you have no idea how to visualize spec of anything, why wouldn't we go fix that problem immediately? Okay, let's continue the site. Even though, speaking of hackers, we're about to get hacked. Yeah, Mumford's treasure map. Let's go. Let's go. This is Spec. What are we trying to look at? We're trying to look at a picture of. Well, so I mean, first off, you know exactly how to view the most important ring in the world, right? This is just I'm being slightly abusive with my notation here, but right, this is Spec Z. Um, how is this Spec? This looks like lines. Yeah, well, I mean, also, I mean, here's one that you know. Here's another one that you know. Spec CX, right? What is this? I mean, it's roughly it's roughly just the complex numbers, right? Plus we have the generic point, which sometimes we call eta, right? Slightly more generally, I mean, spec of this is just CN. Again, we have a generic point as well. Huh? Spectrum of a linear operator also corresponds to spectrum linear operator? What? What the hell are you talking about, Leo? Spec Z is just a disconnected set of primes and the one generic point. Well, no. And so here's the thing. What does it mean to be connected, right? So again, you can't be thinking with your analytic geometry brain. You can't be thinking with your analytic geometry brain. That's gone. That doesn't make sense anymore. Right? That doesn't make sense anymore. Because remember we're working in the Zariski topology, right? So our basic open sets, like our open sets are very large, generally speaking, right? I mean, it's basically like the finite complement topology. It's basically the finite say on Spec Z. It's the finite complement topology, right? So yeah, yeah. All right, back to endomorphisms. Why the hell are we talking about endomorphisms? What is going on? What are you talking about? Say you take kx to end v. What is v? A vector space? What is v? Which is just selecting a linear operator. K? A linear operator? What do you mean? A linear operator where? What? I don't understand. Where I is the kernel. Gives you eigenspace as a nilpotency degree. Okay. Zariski topology is ass. Yeah, sure. Okay, you're over it. Clearly there's some cute trick. Yeah, fair enough. Yeah, that's why we cheated. That's why we cheated. Leo, what's your blog again? What's your blog? Leo lecture. Oh, here we go. Go blog. Where is it? What's it called? What's it called? How do I find your thing? Control K. Hey. I'm K. Anywho, let's get back to the treasure map. You vaguely remember the picture of spec CX from the rising C. Did normal points correspond to linear polynomials? Yes, exactly, right? Because, yes, exactly. So, the one I was just on, huh? At the top? What? The missing linear, what are you talking about? The missing linear algebra for pure mathematics course? That doesn't sound like the right one. Are you sure? Monic Yes, monic linear polynomial. Okay, here we go. What? It is this one? Oh, okay. I guess that makes sense because you're talking about linear operators. What? Where do you talk about this? I don't see a kx. I mean, there's a kx down there. Oh, I see. Is it here? The Jordan canonical form. Yeah, but this is just. I mean, this does not make it clearer to me. I'm gonna have to look this up after, or look forward to your detailed video. But yes, the point is, all of your maximal ideals. I mean, what are the maximal ideals in here? They're just going to be generated by all of your linear polynomials, monic linear polynomials, right? I mean, monic doesn't even really matter here, right? Because you can just shift over by a scalar. Actually, I guess if you have multiple polynomial, no, I mean you're still shifting by unit. So like really, it's not that important. So of course this is in bijection. Of course this is in bijection with tuples. With tuples of complex numbers, right? So that's why we can identify the points with this, and then we have the generic point as well, corresponding to the zero ideal, right? And um, what am I gonna say? Uh, um, what am I trying to say here? Yeah, and then the Zariski topology is basically just the finite complement topology on this, right? Because our basic open sets is the zero locus, or our basic closed sets is the zero locus of some polynomial. So the complement, right? And a polynomial has finitely many zeros, so the complement of that is going to be, just some set with like finitely many points, some big open set with some finitely many points removed, right? So all of our open sets are very big. I mean, okay, these are just the basic ones, but all of our open sets are very big. Yes, there is always a generic point corresponding to ideal. He will never read this. Well, maybe. What does the spectrum of the ring of smooth complex functions on a compact manifold look like? Smooth functions on a complex manifold. Compact on a compact manifold. What does it look like in general? I don't know. That's a good question. But isn't there some also, like, this is the functional analysis perspective that sort of gave birth to algebraic geometry? There's something like compact Hausdorff. There's some duality between functions on compact Hausdorff spaces. So compact. Um, there's some duality here or something. What if I search duality between compact Hausdorff and rings? Something will come up. Locally compact Hausdorff spaces. Yeah, so even better. I mean, it should be. We still should have a correspondence between prime ideals and points of the space, right? Yeah. No, just smooth. Right. Complex differentiable. But yeah, no, complex differentiable is just trivial, right? So that would be silly. What other things make generic points? That would be CX, real smooth functions, which also have max ideals corresponding to points. I don't think it's just CX. No, definitely not. I mean, think about all the functions on the circle. Yeah, I got yeah, real manifolds, but we're allowing complex valued functions. No, that's false, Leo. All constant? I don't think that's true, because wait, didn't you say you aren't asking for complex differentiable? Oh, you do want complex manifolds. I'm confused. Yeah. Holomorphic on compact is all just constant. Yeah. Is every manifold is Hausdorff? Yes, that's true. Is there a good algebraic geometry reason that the Stone-Weierstrass theorem is like that? I don't know. Maybe. Other schemes can be upgraded to stacks. Well, every scheme is a stack. Sort of. Every scheme is a stack, right? So stacks are supposed to be generalizations of schemes. Yeah. Math stacks are a scam. They don't have push and pop. Yeah. I don't see how one would have an algebraic geometry reason for Stone-Weierstrass. Yeah. Well, I don't know. Can I give a recap of what I'm doing right now? Well, we're talking about how to picture the spectrum of various different rings. So spec of a ring is a topological space whose points are prime ideals of the topological space and whose topology is given by something called the Zariski topology. Zariski topology. I'll let you look it up, but you can vaguely... It's kind of the finite complement topology. Not exactly, but... and then the other important piece of data, it's not just a topological space, but we put a sheaf on the space coming from the ring itself. Well, these are affine schemes. Of course, there's more general schemes. But so now, right? Okay, so I mean, these are the two most important pieces that go into our intuition, though, right? We spec CX, we know, yeah, looking at spec C infinity for M compact. Yeah, that is, well, maybe we'll come back to that. Maybe tomorrow. I don't know how much longer I'll stream for. But so the thing is, we want to understand, we're looking to understand spec ZX, right? And so we're gonna go. We should expect there's some sort of combination of these two pictures, right? Of course, spec C is an algebraically closed field, so we can't expect it to for an algebraically closed field, you should roughly think of this as being, just equivalent to that field itself, plus a generic point or whatever. I do have Dr. handwriting, that's true. I should go... I like the dark mode. Leo, that app that you sent that we were both writing on, that you can write and tech, does it have a dark mode? Because maybe I should just switch over to doing that for streams. Check cohomology for CX, maybe later, maybe another time. But yeah, we should get into that at some point. So, but now things can go wrong, right? So the point is, if you're in spec CX, then all of your maximal ideals, sorry, all of your prime ideals are maximal, right? So life is really easy. But of course, now if we're looking at something like spec zx, now we have things like x squared plus 1, right? And whereas before in spec cx, it was very obvious how to just associate each of your ideals with a point in C, right? Now it becomes not so obvious because, you know, now this isn't linear, right? So still all of our integers, you know, determine a point here. So this should look something like, it should have the integers, but now there's something weirder going on, right? Like what points do you ascribe this to? I mean, somehow you're picking up an I and a minus I. So somehow there's like 2 points, well, I mean, it doesn't even live in our base ring, right? So, but this is an interesting idea. Oh, not all integers are points. Right. Not all integers are points. Yes, actually. Uh, that is true. Wait a second. Yeah, that's true. Yeah, I think that's true. Boy, we're real behind stream now, which is the goal. It's always a goal. The generic point 0 in spec Z. Yes. Yes. It does have dark mode. Okay, maybe tomorrow I'll try switching over to that. Manifestation of Stone Weierstrass you've seen says that the closed subalgebras of that separate points for compact Hausdorff for the whole thing of the set. Yeah, not quite the same as the ideals. I'll have to go, if the app is, if you go look at the representation theory live video that I did with Leo. You don't want the server overloaded? Well, don't share the link. It's already in a public video. It's already in a public video on my channel. So, yeah, too bad. I don't know. I could try to hide it on my other streams, but I don't know. What am I gonna do? Really hide it? I don't know. I don't know. K is curvilinear. Yeah. If we have the evident inclusion, then what does that mean for the equivalent affine scheme map? Yeah, I guess. What does that mean? What does that mean? I mean, it's a I guess a cover of sorts, right? Yeah, it's a sort of covering. Some big wild covering. Yeah. Is there some type of embedding map from Galois fields to schemes? Well, yeah, I mean, all of the, this is sort of what I think Growth and Deke did, is that you, a field extension now corresponds to a covering, right, of spec F by spec E, right? And this is where, and now if you know about how in algebraic topology, the fundamental group is just the deck transformations of a cover, then, well, the deck transformations of this cover, perhaps unsurprisingly, based on vibes anyways, turns out to be the Galois group of this cover. From the ATAL perspective. from the ATAL perspective. Probably did the check on the E wrong, because I always do. But you don't know if you'd call it a cover? You mean from CX to ZX? Yeah, I mean, that's probably not the right way to think about it, but I mean, it is technically, it should surject on the primes, right? Is that true? No, maybe that's false. Yeah, maybe that's false. But where were we here? Let's go back to the treasure map. Mumford's treasure map. Yeah, so here now we're starting to better. I mean, we'll go more into the explanation in a minute, but so for this reason, you sort of see we look at spec ZX. We're going to sort of look. There's two axes here because again, from our intuition, we're going to look at things coming from Z, and we're going to look at things coming from the polynomials, right? Because for example. So we know we should be able, if we quotient this out by irreducible polynomials, right? Then we should get integral domains. So we should have a class of points coming from polynomials, but then also, right? If we take the quotient of this by just a prime number, then this becomes the integers mod p. This is an integral domain. So we should also have like points that are somehow coming from spec z. So that's why we're plotting on the axis here. So here we have this generic point, right, which is somehow like dense. And then you see we have on our axes, so above each one of these, right, above each prime, there's sort of like a collection of points corresponding to that prime. But also, right, this, even though it's an integral domain, we can go further, right? Because you could also, so what do we have? We have like ZX modulo a prime. So this is a point, but it's kind of like a fat point because you could keep going because it's not a maximal ideal. So you could toss in some irreducible polynomial, and somehow this is like a thinner point. It's like a more refined point. So that's why we see on this map there's a little blob, right? So the ideal by 2, why is it blobby up here? Well, it's because we toss in an irreducible polynomial, and this is somehow like a thinner point, right? And then the thinnest point possible is like a maximal ideal, right? So that's why we have these points sort of all along here, because it corresponds. And then that's why our y-axis here is polynomials, because it corresponds to sort of tossing in yeah you know what I'm saying? Does this make any sense? Chat is popping off here. Chat is popping off. Like pi gets sent to the generic point. Yeah. Actually, and there's a whole perspective on this. Like, I think actually my friend was telling me that he used something like this before. He was doing some number theory argument, and yeah, there's something like the transcendental, like you're looking over some algebraic field, you look over some like infinite extension, and then like, yeah, the transcendental numbers should get mapped to generic points. And there's something you could frame. There's something he did about framing like algebraic numbers versus transcendental ones in that way. Any wisdom about lens spaces? Sorry, I don't remember much about that. I remember doing some like basic. Aren't lens spaces just like you're looking at? Am I misremembering? But it's just like you're wrapping around a torus a number of times, right? I vaguely recall computing some stuff with that in an algebraic topology course. How do I deal with Galois group versus absolute algebraic closure, like Q bar? Yeah, I don't know. I don't know if that is. Well, I mean, it's all kind of consistent, right? Because like even in like the Galois group, because in algebraic geometry land, like the universal cover may not exist in the same way that it does in analytic topology land. So like the fundamental group, right? The Galois group, the group of deck transformations for the universal cover is just your fundamental group, right? But now this object, if we go in an algebraic category, like if we're thinking about the maps, from what CX to itself or like S1 to itself, given by these maps, right? The sort of universal cover of this becomes exp. But now this doesn't exist in the algebraic category. So what you do instead is, because you can't take this one exact fixed group, what you do instead is you take the limit of all the Galois groups of the covers. And I mean, that's exactly how, now if we go over to fields, like, how is the absolute Galois group defined? Well, it's literally this limit over all the Galois groups. But I mean, from an algebraic geometry perspective, I think Q bar, spec Q bar to Q is just, like probably too crazy. So I don't know if it's helpful at all. I mean, the absolute Galois group is just hard to understand. So, yeah. Where are we here? Yeah. Difference in algebraic properties. Spec C to spec Z might be easier. Yeah. ZX mod P is a generic point, not a fat point. What do you mean by that? It's generic? I don't think that's true. Generic in the sense that if you take the closure, or what? Generic in what sense? Yeah, I mean, okay, maybe algebraic geometers use this in a more technical sense, but I mean, it is a point. It is a point, and it's thick. It's a point and it's thick, right? I mean, that's exactly why there's blobs on these lines, right? It's somehow like a thicker point, right? Um, yeah. Not a point in that sense. What? Fat points aren't generally points. Well, maybe I'm okay. Maybe there's some technical use of fat points that I don't know. But I mean, if you look at the picture, clearly from the picture, it's a thick point, and like psychologically, this makes sense for the reason I mentioned. Yeah. Right. Exactly, and that's a very important map lock that you have there, because we oftentimes uh, yeah, spec of a field is a singleton, but it's a very interesting singleton. Like, again, speaking about fat points and thick points, like, yeah, it's very yeah. So but let me just say, yeah, for lock, this is a very important. Sometimes we call this the structure map, right? So there's also, one will oftentimes consider the category of schemes, over some fixed base scheme, right? And so this is the classic example, right? Or maybe you want to consider, so like, if we want to think specifically about things that look like gluing together patches of affine space, right? In the usual sense. So we're kind of trying to throw out, like, I don't want to glue CX's to like over finite fields, which you could. But if you want to do something where you're just thinking about like sort of complex algebraic varieties, things that sort of look like this, you might consider the category of schemes over over C, and we sometimes call this the structure map. So we're thinking of this as being a more complex thing, but yeah, spec. Yeah. How much of pure math is useful for new technologies? Not the majority of it. Spec of a field is a singleton. Yes, exactly. But the point is like a geometric point. So spec of an algebraically closed field, you should somehow think of as being like a true. This is like a true point. Yeah, this is like and somehow other points are like fake points. So you should think of other points are like they're thick somehow, right? There's more going on because, for example, like the étal fundamental group, right? The étal fundamental group of like spec some finite field extension is equivalent to this Galois thing, right? So there's somehow like there's or oh gosh, did I write this the wrong way around? No, spec E. Did I write this the wrong way around? Maybe I wrote this the wrong way around. Maybe I wrote this the wrong way around. But yeah, the point is overall algebraically closed fields have the most true points, basically. Yeah. Oh yeah, I guess I wrote it. I guess it should be. I guess isn't it the other way around? Am I wrong? Am I mistaken? Shouldn't it be this Galois group? We might even have to take this to be separable or something. Okay, I guess I'm gonna have to look into this. How do you make a singleton interesting? Well, yeah, but remember, a scheme is not just the topological space, right? Remember, a scheme is a locally ring space, so it's a topological space together with a sheaf, right? That's where your geometry comes from, right? It's just like how if you took, what is a smooth manifold? Well, it's a topological space, yeah, but it's a topological space with a very important set of data being the atlas, which has all of these these functions with these differentiability conditions on them. And so, there's a huge difference between differential geometry and topology, right? There's so much more going on in differential geometry. So then the same thing, if you're just thinking of spec of a field as just the point, well, you're missing all of the geometry actually, because the geometry is all in this ring. Is it all in this sheaf, right? And what's going on in that sheaf? It's the field itself. And of course, field theory has like a lot of rich structure to it. So, yeah. Yeah. Yields, but he's talking about evaluation. Oh, is that back when I was yapping about other stuff? K is calling literally every notion of a point a fat point. Is that true? I don't think that's what I'm saying. We have fundamental group of specs now. Yes, that's what I was saying before. You just take the right. The fundamental group of a topological space is equivalent to the deck transformations of its cover, and so this is purely topological. This is purely in like analytic topology land, right? What is this? So we write Gal in analogy with Galois theory because this is the set of automorphisms of the cover, right? Or the group of automorphisms of the cover, right? So now loops don't make sense in schemes, but covers still make sense, and so do the automorphism groups. And then that's how we define these things. Yeah. Yes. Yes. He showed that from just a point you can construct the category of commutative algebras. So I'd argue that points are very important. Yeah. Tanaka was your first algebra prof. Damn. It's hard to think about since a singleton manifold is super boring. Yes. But you suppose an infinitesimal one is interesting. Yes. It's all in the sheaf. Geometry is stored in the sheaf. Yeah. Anywho, I guess that's gonna do it for today. I got stuff to do. I got places to be. So thank you all for joining me, and I suppose I should say QED.